Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. As I mentioned in episode A1, two important applications of thermodynamic theory are analysis of process efficiency and prediction of phase equilibria. Last week we discussed process efficiency. So let's now turn to the problem of phase equilibrium. In particular, systems with just one component, but two or more phases. To frame today's discussion, let's return to a thread we started a few weeks ago on the issue of phase separation and why it occurs. In modeling a 2D Lennard-Jones fluid, we found that non-ideal behavior of gases and supercritical fluids could be modeled fairly accurately using mean field energetic interactions, as embodied in the van der Waals equation of state, for example. However, below the critical point, this approach breaks down, predicting non-physical behavior, and failing to predict the formation of two phases. This observation set us on the path toward understanding entropy and the second law. Now that we understand a bit more about both, let's circle back and try to explain what's going on here. In particular, why does the system split into two phases, and why these particular phases with these particular phase-intensive properties? Instead of approaching this question generally, I think it's actually helpful to first examine a very specific case where we can quantify internal energy and entropy and break down, step by step, why phase separation occurs. As I'll show you, this approach also leads to some useful physical insights that help us understand how to formulate equilibrium relationships more generally, including the concept of something called Gibbs free energy. The specific system I'd like to consider is a group of 492 2D Lennard-Jones molecules with a molecular volume of 7.9 and a temperature of 0.40. Represented on the left is a hypothetical state, predicted by the van der Waals equation based on its volume and temperature with a pressure of P equals 0.024. The configuration shown here for state 1 was generated artificially by taking a system at a much higher temperature and then suddenly cooling it to T equals 0.4. However, after the snapshot was taken, the molecules began to stick together, reducing potential energy and increasing kinetic energy. In order to keep the temperature fixed at 0.4 during this process, I continuously readjusted the temperature by removing small amounts of kinetic energy. Eventually, the system came to equilibrium in state 2, shown on the right. The actual equilibrium pressure is 0.0073, and the system splits into two phases. The configuration shown here is one configuration of this equilibrated state. The question I'd like to address is why state 2 is stable, while state 1 is not. Now that we have some understanding of entropy, let's try to calculate the entropy and internal energy of these two states, and try to rationalize why state 2 is favored by the second law. According to the second law, isolated systems can only increase in entropy, never decrease. However, just looking at these two systems, we would expect state 1, if it was stable, to have a higher entropy than state 2. This is because at the same temperature, state 2 is more constrained by intermolecular forces, much like a membrane holding the molecules in place. Another way to think about this is that state 2 has lower internal energy, so with the same volume must have lower entropy. But if the entropy of state 2 is lower, why does the system evolve from left to right and not right to left? In fact, why would any system with a single homogeneous phase ever split into two phases, given this always reduces entropy at a given temperature? The resolution to this paradox is that when the system evolves from state 1 to state 2, the system is not an isolated system. It's a closed system. This is due to my addition or removal of energy to maintain temperature fixed at T equals 0.4. This energy exchange is the physical equivalent of placing the system in a constant temperature bath of T equals 0.4 and allowing heat to exchange in or out in order to maintain fixed temperature. Since the molecules in state 2 are more clumped together, the potential energy of state 2 is much lower. Yet the temperatures of both states, and thus the kinetic energy, are the same. This implies that the internal energy of state 1 is higher than state 2. Thus, to evolve from state 1 to state 2, the system must reject a lot of heat. This implies a significant increase in the entropy of the surroundings, which favors phase separation. So it seems we have two competing effects at work here. By condensing at constant temperature, the entropy of the system decreases, but the entropy of the surroundings increases. Which of these effects dominates? Let's employ some of the tools we've learned the last few weeks to calculate and compare these entropy contributions and see for ourselves. Let's start by defining a reference state for internal energy and entropy. In the simulation we've been using, internal energy is defined as the sum of kinetic and potential energy. Thus, the simulation already provides a reference state for internal energy. U equals 0 when T equals 0 and V approaches infinity. This is fine for internal energy, but for entropy, this reference state is problematic. Since we expect entropy to scale as the log of volume and the log of temperature, we can't really pick 0 or infinity as a reference state. Thus, for entropy, let's define S equals 0 at T equals 0.4 and V equals V infinity, where we set V infinity to a very large value, where the gas is close to ideal, for example, 1000. With these selections, we can express U as Ek plus Ep, while S is the integral of Cv over T dt plus R log of V over V infinity, plus entropy departure. As long as the system remains single phase, we found that the 2D fluid can be modeled fairly well using the van der Waals equation. As we've discussed, this model predicts that the potential energy equals minus A over V. Meanwhile, kinetic energy is just T in the dimensionless units of the simulation. For the entropy, we need to calculate the entropy departure for the van der Waals equation. You'll learn exactly how to do this in Chemie 326. But for now, let's just use the result, which is that the entropy departure scales as the log of the free volume, V minus B, divided by V. Meanwhile, Cv equals 1 and R equals 1 in the dimensionless units of the 2D simulation. Plugging in numbers for T equals 0.4 and V equals 7.9, we get values of 0.15 and minus 4.98, respectively, for the internal energy and entropy of the fluid in state 1. Okay, so what about state 2? Since state 2 is a two-phase system, all system-intensive properties of the system, including V, U, and S, will be a quality-weighted average of the intensive properties of the individual phases. Here I'm using Fg, the phase fraction of gas, as the symbol for quality, since I'm using Q for heat. Note that we actually control the total volume and energy of the system, so know these from the simulation conditions. Thus, by incorporating the properties of the individual phases, we can calculate the quality, and then use this value to calculate the entropy. The intensive properties of the individual phases we can gather from the PV and PU diagrams we studied previously. At T equals 0.4, the molecular volume of the saturated gas is about 40. The liquid is a bit harder to tell, since the pressure spikes upward over a range of volumes due to the wall effects. But if we arbitrarily set the saturation line where the pressure is 10 times the saturation pressure, we estimate a value of about 1.5. The internal energy is a bit easier to interpolate, yielding values of minus 1.7 and plus 0.1, respectively, for the saturated liquid and gas. Calculating quality based on either the total internal energy or volume, we obtain results that agree to two significant figures, with quality equal to 0.17. This agrees fairly well with estimates based simply on counting the number of molecules in the gas phase. But this number varies so wildly, it's probably better to use the calculated quality since it represents an average. We'd now like to use this quality to calculate the system-intensive entropy in state 2. But to do this, we need one more step, which is to estimate the entropy of the two individual phases. We've already discussed how to handle the gas using the van der Waals model. At a temperature of 0.4 and a volume of 40, the entropy of the gas is minus 3.25. But what about the liquid? It's unlikely the van der Waals equation will be sufficiently accurate. Instead, let's consider a hypothetical path where we reversibly and isothermally condense the gas to a liquid at constant pressure. In this case, delta S will be given by Q over T, where Q we can work out using the first law from delta U, and the work, which is P delta V. Plugging in numbers, the heat evolved by condensation is about 1.52. Dividing by the temperature, we obtain delta S of minus 3.8. Adding to the entropy of the gas, we get a total entropy for the liquid of about minus 7. Putting everything together with quality of 17%, the entropy of the system is about minus 6.4. Returning to our comparison, we finally have the numbers we need to determine the net entropy change of the universe, going from state 1 to state 2. As we expected, the entropy change of the system is negative, with a value of about minus 1.4. However, the internal energy change is about minus 1.5. This implies that to go from state 1 to state 2, we must release 1.5 units of heat to the surroundings at temperature 0.4. This implies an entropy increase in the surroundings given by 1.5 divided by 0.4, which is plus 3.8 units of entropy. Adding the entropy change of the system, which is minus 1.4 units, we obtain a net change in entropy of the universe of plus 2.4, which is strongly positive. This means that phase separation is strongly favored by the second law, which is why it occurs spontaneously in the experiment described here. To generalize the effect we're calculating here, consider any closed system at defined temperature and pressure. The question we'd like to ask is whether it will evolve in any particular way at that temperature and pressure by exchanging heat and work with the environment. As we just saw in our test case, we expect the system to evolve if the net change of entropy of the system plus surroundings is greater than 0. Or to put it another way, the system will continue to evolve in some direction or another until the entropy of the universe reaches a maximum. Focusing on the system and applying the first law, we can say that any internal energy change the system undergoes must be the sum of the heat and work done on the system. Since we have fixed the pressure, the work will just be equal to minus P times delta V. Solving for Q, we can say that the heat input must equal delta H. But now let's look at the surroundings. If we absorb a given amount of heat, the entropy change of the surroundings will be minus Q over T, which in turn is minus delta H of the system divided by T. Substituting into our inequality, we find that delta S minus delta H over T of the system must be greater than 0. Or rearranging, the quantity H minus Ts of the system must decrease. This is interesting since we have now embedded the effects of the heat flow to or from the surroundings into a property of the system itself. This means that if we have a model for enthalpy and entropy of our system, we can predict if it will spontaneously evolve from one state to another at fixed temperature and pressure, without explicitly considering what's happening in the rest of the universe, other than helping to maintain temperature and pressure at fixed values. The quantity H minus Ts, which like H and S is an extensive state property, is usually called the Gibbs free energy, named after the American thermodynamicist Josiah Gibbs. Gibbs was a contemporary of Ludwig Boltzmann and made enormous theoretical contributions to classical thermodynamics, particularly the concepts of free energy and chemical potential, as well as the Gibbs phase rule. What the Gibbs free energy allows us to do is basically restate the second law in a more useful form for closed systems of defined temperature and pressure. At fixed T and P, a system will always evolve spontaneously to minimize its total Gibbs free energy. Stated mathematically, the second law simply becomes delta G is less than 0. To see how the Gibbs energy is useful for predicting phase stability, consider a fluid that obeys the van der Waals equation. The molar Gibbs free energy will be given by U plus PV minus Ts. Thus, let's imagine we establish a reference state for U and S in the ideal gas region at temperature T0 and large volume V0. To express U and S at any other point, we can integrate heat capacity from T0 to T, and then determine the internal energy and entropy departure going from an ideal gas at V0 to a non-ideal fluid at volume V. The result, after adding U, PV, and minus Ts, gives the expression shown here for G. What does this function look like? Shown here is G versus P at fixed temperature, where I have taken the parameters CV, R, A, and B from the results of our simulation of a 2D Lennard-Jones fluid. We can see that for T equals 0.6, shown in red, which is above the critical point, G increases monotonically with P. This means that at any given pressure, there is only one possible value of G, which the fluid will have as a single phase. However, at T equals 0.4, shown in blue, which is below the critical point, G has multiple solutions over a range of pressures up to about 0.02. The individual branches of this function correspond to gas, liquid, and a hypothetical third phase, which is also predicted by the van der Waals equation. For example, at P equals 0.005, these three phases have values of G spanning 1.85 to 2.25. Which phase is which? To understand this, it's helpful to consider how G will vary with pressure for an ideal gas versus a liquid. Recall for an ideal gas, H is only a function of temperature, while entropy scales as minus R log of P. Thus, G equals H minus Ts should scale as a constant plus RT log P, corresponding to the branch shown here. Meanwhile, for a dense incompressible liquid, H and S are both approximately independent of pressure. But H scales with PV, which on a log plot can be expressed as a constant plus V times e to the log P, which is an exponential growing function, corresponding to the branch shown here. That leaves the third branch as a fluid of intermediate density between gas and liquid. This is where the second law comes into play. At any given temperature and pressure, the system can and will exchange heat and work with the environment in such a way as to minimize its Gibbs free energy. Thus, of the three possible phases, G is minimized when all the fluid forms a phase with the minimum molar Gibbs free energy. That means that below a pressure of about 8 times 10 to the minus 3, the gas is the most stable phase. Above a pressure of 8 times 10 to the minus 3, only liquid is stable. Nowhere is the third hypothetical phase stable, so it never forms. Also, there is one point at P equals 8 times 10 to the minus 3 where both the gas and liquid have the same molar Gibbs free energy, and thus neither is favored over the other. This is the saturation pressure, where both phases are equally stable. Revisiting the results of our MD simulation and looking along the T equals 0.4 isotherm, we observed a saturation pressure of about 6 to 8 times 10 to the minus 3 in fairly close agreement with a point where G gas equals G liquid. Thus, for the set of van der Waals parameters chosen here, the value of Psat equals 8 times 10 to the minus 3 is in fairly close agreement with our MD simulation. However, here we did not simulate it. We calculated it using nothing but the heat capacity and the van der Waals equation, including the additional constraint of the second law through the Gibbs free energy. That's actually pretty astounding if you stop to think about it. Okay, so imagine we have a real liquid and a gas in a piston cylinder assembly. What are the generalized conditions under which these two phases will remain in stable equilibrium? We've already discussed two of them. We know that due to thermal and mechanical equilibrium, the two phases must share the same temperature and pressure. But what prevents the system from evolving completely to one or the other phase by exchanging heat and/or work with the environment? To understand this, consider the molar Gibbs free energy of the system, which, just like any other state property, will be a quality-weighted average of the properties of the liquid and the gas. According to the second law, delta G will always seek a minimum. Thus, if G gas is less than G liquid, the system will evolve until it is entirely gas. On the other hand, if G liquid is less than G gas, the system will evolve until it is entirely liquid. The only way for the system to remain stable with two phases present is if G gas and G liquid are the same. Another way to see this is to consider the enthalpy and entropy of a gas and liquid, which are already presumed to be in equilibrium. If these phases are in equilibrium, then we can calculate delta H and delta S between them using a reversible transformation. Thus H gas will be H liquid plus delta H of vaporization, and S gas will be S liquid plus delta H of vaporization divided by the equilibrium temperature. Expressing G gas as H gas minus TS gas, and substituting, we see that G gas and G liquid must be the same. Finally, a third way to think about this, as we did previously, is directly in terms of the entropy of the universe. If G gas equals G liquid, then any reduction in the entropy of the system due to condensation of the gas to the liquid is accompanied by a decrease in enthalpy that exports heat to the environment and results in an equal and opposite increase in entropy of the surroundings. Thus, the overall entropy of the universe is maximized when G gas equals G liquid. How do we reconcile this mathematical condition of equilibrium with the degrees of freedom based on Gibbs' phase rule? Consider the equilibrium of any two phases, alpha and beta, containing a single component. Up to this point, we've said that a condition of equilibrium is that T alpha equals T beta and P alpha equals P beta. But mathematically, this is a system of 4 variables and 2 equations, which would have 2 degrees of freedom. Yet Gibbs' phase rule says that if we have 2 phases, we only have 1 degree of freedom. So what mathematical relationship is missing? Based on the previous considerations, we need to add that the Gibbs free energy of each phase must be equal. That adds 2 more variables and 1 equation, pushing our degrees of freedom up to 3. However, if we express each of these Gibbs free energies in terms of the enthalpy and entropy in each phase, and recognize that H and S are functions of T and P in each phase, we have a system of 10 variables and 9 equations, which has only 1 degree of freedom. So there you have it, Gibbs' phase rule finally justified, mathematically. This all leads to a general prescription, shown here, for formulating problems involving phase equilibrium with a single component. Although not all of the following steps are necessary in every problem, you can think of this as a checklist for all the elements that need to be in place in some way. First, to define Gibbs free energy, we need to directly or indirectly define a reference state for enthalpy and entropy. We then need a set of physical assumptions or models describing each phase. For example, it's an ideal gas, an incompressible solid, or a fluid obeying a particular equation of state. Third, we must construct a representation of H and S versus temperature and pressure in each phase individually, so that we can express G versus temperature and pressure in each phase. Finally, by imposing the conditions of equilibrium, we can solve for unknown state variables in terms of quantities we know or wish to specify. In order to make this a bit more concrete, let's now go through a couple of examples where we use the equilibrium relationships between 2 phases to make a prediction. The first example I'd like to discuss is the general problem of predicting saturation pressure of liquids. This problem is not only important for understanding behavior of pure substances like H2O, but is also a piece of the larger problem of predicting vapor-liquid equilibrium in mixtures. In particular, let's say we know the normal boiling point of a liquid at 1 atmosphere. We'd like to understand or predict how the saturation pressure will vary as a function of temperature. In order to keep things relatively simple, let's assume we're talking about modest pressures, where we can assume the liquid is incompressible, and that the gas is ideal. First, we need to define a reference state for H and S. We know the normal boiling point, so let's define our reference state as a liquid at P0 equals 1 atmosphere and T0 equal to the normal boiling point. We then need to express the enthalpy and entropy of both gas and liquid as a function of the conditions we wish to change. In this case, both temperature and pressure could change, so we need to consider both. Since the liquid starts in equilibrium with a gas under the conditions of our reference state, to determine H and S of the gas, we can construct a reversible hypothetical path where we boil the liquid at temperature T0, heat or cool to a new temperature T, and then change the pressure from P0 to P. As we've discussed previously, the first leg of this path involves the standard enthalpy and entropy of vaporization, defined at the normal boiling point. The second leg requires us to integrate the ideal gas heat capacity. Finally, for the third leg, if we continue to assume an ideal gas, delta H is 0, and delta S is minus R log of P over P0. Meanwhile, for the liquid, starting from our common reference state again, we need to heat or cool to a new temperature T, and then change the pressure from P0 to P. The first leg involves integrating the liquid heat capacity. But if we're assuming moderate pressures, delta H and delta S along the second leg will be 0 for an incompressible liquid. Note that the pressure and temperature we want to consider might be lower than in our reference state. In this case, the upper path, which involves boiling the liquid to a gas, cooling the resulting gas below its saturation temperature, and then lowering the pressure, is an entirely hypothetical path that could not actually occur. But that's okay. Our objective here is to map out the properties of these two phases individually, as if they could exist as a single phase at a given temperature and pressure. Once we've done that, we can impose the equilibrium constraint to determine if and under what conditions each phase will be stable relative to the other one, including solving for values of T and P where the two phases can coexist. Adding up delta H and delta S for each leg, we end up with the general expressions shown here for enthalpy and entropy. Recalling the definition of the Gibbs free energy as H minus Ts and substituting, we get the free energy of each individual phase as a function of T and P. Thus, at any given set of conditions, we could calculate these quantities to determine which phase would have the lower value of Gibbs free energy and thus be more stable relative to the other. At equilibrium, the value of these two functions must be equal. Imposing this and rearranging a bit, we get an equation relating pressure to temperature at equilibrium. There are quite a few terms here, but we can see what appears to be a principal dependency of the log of pressure versus reciprocal temperature. To better see what's going on, let's take a derivative of log P versus 1 over T, which results in the expression shown here. The term on the right contains delta H0 plus the integral of the difference in heat capacity between the liquid and gas. This corresponds to the change in enthalpy along a hypothetical path from T to T0 as a liquid, boiling at the reference temperature, and then increasing the temperature of the gas back to T again. Since H is a state property, this is equivalent to the enthalpy of vaporization at equilibrium at temperature T. Substituting, we get the much simpler relationship shown here, called the Clausius-Clapeyron equation. This equation predicts that the local slope of log P versus 1 over T along the coexistence curve will be equal to the enthalpy of vaporization at that temperature divided by R. This is a general result that holds for any single component, subject to our original assumption that the gas is ideal and the liquid is incompressible at moderate pressures. If we make the further assumption that the enthalpy of vaporization is approximately constant, the Clausius-Clapeyron equation reduces to d log P d1 over T being equal to minus delta H0 over R, which is a constant. This can be directly integrated to obtain a linear relationship of log P versus 1 over T, known generally as an Arrhenius dependence. Many quantities besides saturation pressure, including kinetic rate constants for example, depend on the exponential of the reciprocal temperature, so it's common to see data presented as the log of something versus 1 over T. This is known generally as an Arrhenius plot. Shown here is an Arrhenius plot of the saturation pressure of H2O as measured using our transparent piston cylinder assembly from episode A4. Plotted along with our data are data from the steam tables, shown as a dark black line. The dotted line is the dependence predicted by the Arrhenius dependence we just derived, based on the enthalpy of vaporization at 100 degrees C. As you can see, the result is fairly accurate, but fails to capture the slight curvature in the data. Over this temperature range, this curvature is due to the enthalpy of vaporization being a slight function of temperature. However, given the close agreement here, a common approach to correlating the saturation pressures for real substances is to correct this basic Arrhenius dependence with some additional empirical parameters. One of the most common models is the Antoine equation, shown here. Like many other thermodynamic correlations, its underlying form is based in theory, but the parameters actually used in practice are obtained from fits to measured data. These parameters can be found for many substances in Table A1 of our textbook. The Antoine equation is amazingly accurate, in part because some of the assumptions leading to an Arrhenius relationship partially cancel each other. On the problem set, I ask you to explore this issue in a bit more depth for the case of H2O. The second example I'd like to show you relates to solid-solid equilibrium and prediction of phase transformations in solids. Due to the production of videos for this class, I spent quite a few evenings and weekends working, forcing my spouse to make excuses to our kids for my antisocial behavior. My cliché existence is nicely captured by this cartoon, in which the patriarch of a family of lumps of coal arrives home as a diamond due to all the pressure at work. This cartoon is based on a commonly held belief that coal, derived from Paleozoic plant materials, will eventually form diamond, a dense form of carbon with an isotropic tetrahedral crystal structure when subjected to sufficient pressure, temperature, and time in the Earth's crust. How much pressure does carbon have to be put under to drive it to becoming diamond? To answer this, let's try to model the equilibrium between graphite and diamond at room temperature. Besides assuming constant temperature, let's also assume that both solid phases are incompressible, even at fairly high pressures. Here's some data. At 25 degrees C, the density of diamond is 3.51 grams per centimeter cubed, which is much higher than the density of graphite, which is only 2.26 grams per centimeter cubed. Let's say that we also know the standard Gibbs free energy of the phase transition from graphite to diamond, which at 25 degrees C is 2,866 joules per mole. I'll get back to exactly what this number means in a moment. Following our previous procedure, let's pick a reference state of 25 degrees C and 1 atmosphere, where the most stable form of carbon is graphite. To get to graphite at higher pressures, we only need to do one thing, which is to increase the pressure. Since we've assumed the graphite is incompressible, we expect the change in internal energy and entropy to be zero. However, the pressure in this case could be quite high, so delta H could be non-zero due to the change in PV, which for an incompressible solid would be V times delta P. The volume in this case is the volume of graphite, which is higher than in diamond due to its lower density. To get to diamond at high pressure, we need to first make diamond and then raise the pressure. Unlike the example we looked at earlier, our reference state in this case is not a saturated state representing equilibrium between diamond and graphite. At 25 degrees C and 1 atmosphere, graphite is much more stable than diamond. However, diamonds can still exist at 25 C and 1 atmosphere due to the limitations of kinetics in converting to graphite, which are very slow. So we can still measure the properties of a diamond at 1 atmosphere, including the heat capacity and thus enthalpy and entropy. These are tabulated in the literature, from which we can calculate delta H0 and delta S0 for the transition from graphite to diamond. Note that because the graphite and diamond are not in equilibrium at 1 atmosphere and 25 degrees C, we cannot say that delta S is delta H over T0, as we did for saturated H2O. As with graphite, increasing the pressure from P0 to P is not expected to change the entropy, but will change enthalpy due to the PV term. In this case, the volume, V diamond, is smaller than V graphite due to the higher density of diamond. Putting things together, the Gibbs free energy of graphite will be given simply by the graphite molar volume times delta P, reflecting the increased enthalpy at higher pressures. Meanwhile, the Gibbs free energy of diamond will be delta H0 minus T delta S0 plus the diamond molar volume times delta P. Since delta S0 is not equal to delta H0 over T, delta H0 minus T delta S0 will be non-zero. This quantity is the standard Gibbs free energy of the phase transition from graphite to diamond, the parameter I introduced earlier as part of our available data. The standard Gibbs free energy of a reaction or phase transition is often tabulated in the literature. Its large positive value in this case, nearly 3 kilojoules per mole, reflects the much greater stability of graphite relative to diamond at 25 degrees C and 1 atmosphere. In fact, the only thing preventing diamond jewelry from spontaneously decomposing to graphite, or for that matter reacting with air to form CO2, is the very slow kinetics. Equating the two free energies, we finally see what's going on here. Due to the higher molar volume of graphite, its enthalpy increases with pressure more steeply than the enthalpy of diamond, and this eventually compensates the higher free energy of the diamond under standard conditions. Solving for pressure, we find that it will be inversely proportional to the difference in the molar volume. Converting density to molar volume and plugging in numbers, we get a pressure of about 15,000 bar. That is a very high pressure, much higher than any terrestrial plant debris on Earth has ever been exposed to. So the idea that diamonds come from coal is actually a myth. Diamonds form from Precambrian minerals in the upper mantle, about 90 miles beneath the surface of the Earth, where pressures are high enough to stabilize diamond relative to other phases of carbon, and the temperatures are high enough for reactions to proceed at a finite rate. The diamonds are subsequently transported to the surface of the Earth by deep source volcanic activity. Finally, I'd like to make a comment about a common source of confusion surrounding standard free energies tabulated in the literature. Often in freshman chemistry, we're introduced to endothermic and exothermic processes and told that the direction of a process can be determined by the sign of delta G, which is found tabulated in the back of a chemistry book for various reactions and processes. If delta G is negative, then the driving force for the process is in the forward direction, and it will occur spontaneously. If delta G is positive, then the process will be inhibited or occur in reverse. However, what about processes at equilibrium? According to the discussion here, delta G for any process at equilibrium, it must be 0. So how can any of these tabulated processes come to equilibrium if delta G is not equal to 0? The resolution to this apparent paradox is that the tabulated values of delta G you find in the literature is the value of delta G under a certain set of standard conditions of temperature, pressure, and composition. It's not the value of delta G generally speaking. For example, consider the case we just examined. The large positive value of delta G0 of the graphite to diamond phase transition implies that diamond is unstable relative to graphite at 25 degrees C and 1 atmosphere. But when we allow the pressure to vary, we found that at sufficiently high pressures, we can have both phases in equilibrium with delta G equals 0. The Gibbs free energy of a reaction or phase transition is often tabulated under standard conditions, even if one or more of the reactants or phases is unstable under standard conditions. In this case, the tabulated value represents an extrapolation from conditions where reactants or phases are stable. As I've mentioned earlier, a useful feature of thermodynamic theory is its self-consistency, an ability to make accurate extrapolations of molecular behavior based on only a small amount of data. A prime application of this is understanding and predicting single component equilibrium.